Okay, so revisiting this code that I was writing regarding Goldbach's conjecture, which again says every even number greater than 2 can be expressed as the sum of two primes. Again, the purpose of this program was just to basically generate just, well, thousands or even tens or hundreds of thousands of test cases supporting that conjecture. So let's actually give a little demonstration of the functionality before we start going back to the code. I'm going to drag my output up here. That's a little too far. Okie doke. There we go. And let's run. And it's going to prompt me to enter in a number. That number is going to serve as sort of a maximum or an upper bound to generate prime numbers and then generate by brute force every possible sum. So let's say we go up to like 17. All right, so here's what is output. If you notice these equations here, we have the left-hand side is fixed at a prime number, such as 2, while the right-hand side then loops from 2 all the way up until our input value, which was 17. So 2, 3, 5, 7, 11, 13, 17. On the right-hand side, we see every sum of pairing up those prime values. Then it moves the left-hand side of the addition into the next prime value up, in this case 3, and repeats the same process where it loops through every prime value. So really we're generating every possible test case for summing two prime numbers. Additionally, what this program does is it captures all of these sums, it puts it into a list, and then it starts, it only puts it into the list if it's not odd, meaning it's an even number, because we're trying to demonstrate test cases that support Goldbach. Oops. Anyway. So this actually shows 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and then if you notice it shows 34, but it does not show 32, meaning we have not generated the number 32, the even number 32, given prime summing up, all these prime numbers in every possible way from 2 to 17. So there is a little gap there. We did generate 34, that's 17 plus 17, but we did not generate 32. Yeah. It also keeps track of the number of sums that we actually calculated, because this is not the complete number of sums. This is not including repeats, and it's not including odd numbers. All right, shrinking our output here. Let's go to our code. So what I did, after much consideration, because this is a big, this was a big decision to make always, and that's, do I use an array or do I use an array list? I decided to switch to an array list. Now, I'm not sure why, but for some reason, there's a good explanation for it, I'm sure. I have to look it up, but we usually define the left-hand side of this assignment statement to say list of integers, whereas we have the right-hand side to use the constructor of array list of integers. Now, list is a more general form of array list. Like array list, if I'm not mistaken, is an extension of the list, or maybe it implements the list interface is what I'm thinking. Anyway, we normally call that an array list. Integer, if you notice now, is capitalized with a capital I. That's because we're using a class in Java. It's a wrapper, what's called a wrapper class. That's W-R-A-P-P-E-R. And basically it uses that to wrap around Java's built-in primitive digits, such as int, long, and byte, and all that, in order for it to be functional with lists. But newer versions of Java, and I say that meaning probably for the past several years, newer versions of Java now have what's called auto-boxing and unboxing. So integers are automatically either typecast down to ints, or ints are cast as integers, or they're basically interchangeable. So we have our prompt, we have our scanner. By the way, I did have to add a few more import statements here to use lists. I had to import java.util.list, java.util.ArrayList. I did end up using a function from the collections class, so I imported java.util.collections. And then, of course, I have a static input statement, which is very different. It just basically means that I no longer have to use the prefix system dot. So my output is then out.print, out.println, and my input is simply in instead of system.in. Anyway, I grab the user input, then I jump into a loop. My loop control variable in this case is a. So I establish a to be 2. It goes all the way up until and including num. If no, well then, yeah, including num. One number at a time, and then it jumps and asks, is A prime? If it is, it goes into another loop and says, is B prime? Oh, this other loop uses loop control variable B, so it's going to loop from 2 all the way to num as well. Sort of like, I mean, they're very similar loop conditions and loop initialization variables. So, I mean, the loops here are initialized very much the same. So when I actually count the calculations in its current form, it's literally giving me always a perfect square. In fact, down here, 49. 49 is 7 squared. What that meant, so it's always going through this as many times as it needs to. So that's not very good for efficiency, but we'll worry about that later. So we have if A is prime, start a new loop. If B is prime, then I built in a new variable here, called it sum, and gave it the value A plus B. Printed out the actual values of A plus B, as you can see here, and an equal sign. And then here I put if sum mod 2 equals 0, meaning sum is an even number, and sums not contains sum, meaning in our list of sums we do not yet have our current sum. Then we'll add in this sum, this new sum. Print out the sum, increment the counts of counting the number of calculations. Then I print sums. I have collections.sort. This is why I had to import the collections class. So I had collections.sort on our list, our array list of sums. Then when you do an out.println on sums, it invokes the toString method, as it always does for objects. And the way that array lists are defined as objects, it prints out the list surrounded by rectangular brackets. Then I do my calcs. The only actual function that I've used here then is prime. So the rest of this is not very functional, it's more procedural, and it's also very inefficient in its current formula, in its current state, because it's basically looping is prime causes it to loop. So I have is prime inside of my first loop, then I have is prime inside of my second nested loop, so I'm really nesting a whole lot of loopage. Looping. I'm nesting a lot of loops here, so it's going to come out to be pretty inefficient. And let's see how it runs for a larger value. Let me, again, increase my output window here. There we go. Let's run it. And let's just see it work its magic for a very large value. When I say very large, based on my experience here, let's say something like 1,500. So what you can see happening is the right-hand side is looping from 2 all the way up to 1,500 and increasing that every single time. while the left-hand side stays fixed at the first prime value, again, looping from 2 all the way up to 1500. So what you're getting here is you're getting every possible pair of prime numbers, again, in a very brute force style, and then taking their sum, throwing all those sums into a list called sums, printing that out, and checking that every single even number is generated, again, up to a certain point, because you cannot demonstrate theorems or conjectures like that about infinite numbers because of the finiteness, what I'm trying to say, of computer memory, computer storage, and of course the time that it takes computers to do calculations. As you can see here, this has been running for a little while now. And my my left-hand prime is at 1153, 1163, 1171. While our right-hand primes are also looping for every time that our left hand is fixed. I'm going to point out that the number of calculations done here, the number of sums taken, should be however many prime numbers there are between 2 and 1500 squared. And I also want to point out that if you notice that it's running slower now, that's by design, because now every time it's checking for primality, it's having to loop even more and more and more. Okay, our output has executed. I'm looking at my list of sums, and I see 4, 6, 8, 10, 12, 14, 16, 18, 20. I'm not going to keep reading that list, but I'm going to say ... in my brain. And if you go to the end of the list, I'm looking at 2998, but I do not have the previous even number, 2996. I do have 2992. I don't have 2990. So you'd have to kind of look at the end of this list now and look for the gaps to properly say which even value was this demonstrated up until. Number of sums was 57,121. I'm sure that's a perfect square. I'm not sure what it is, or I'm not sure what the square root of it is. And there you go. So, I mean, this is, again, test cases for a, as of now, still unsolved mathematical conjecture, Goldbach conjecture. And you can do this, and you can keep doing it for till the end of time. And you're not going to solve Goldbach conjecture in this manner. This is simply an exploration into how we can use functional computing and programming languages, and some of the math features specifically here in Java, and the features associated with lists, input and output, and at least one procedure or function that's defined using a parameter. This seems to demonstrate all those things, and it's just pretty interesting.